Hello, welcome back. We're going to get started right now. I know that some of you have a couple of questions from the homework. I'm also going to go over two questions in the homework. Maybe you have similar questions as well. Hopefully that will help. So the first question I want to go over is it's in the optional homework. I don't think it's in the current homework, just in case you're interested. So the question is evaluate the limit as x goes to 0 of e to the x minus 1 minus x over x squared. So so that's a couple ways to find the limit. One is that you can try to use L'Hopital's rule, because if we plug in 0 directly, right, we get an e to the 0 minus 1 minus 0 divided by 0 squared. So it turns out to be 0 over 0. We cannot determine the limit. So you can use L'Hopital's rule. That should work. But since we talk about power series, we can actually try to use power series here. And here, the limit x goes to 0 is sort of the key to determine which power series we use. And x goes to 0, if we use Taylor series, that will be what we call Maclaurin series, right? So because we take the limit as x goes to 0, we can use Maclaurin series, or we can use Taylor series at x equals 0, either way, right? So what we're going to do is that we're going to expand, before we take the limit, we're going to expand e to the x using Maclaurin series, substitute into the limit, and then simplify. So we're going to use Maclaurin series for e to the x before take the limit. So we know that e to the x Maclaurin series is sigma n from 0 to infinity, x to the n over n factorial. If we expand this, so that will become the first term 1n equals 0, we just get 1. The next term we get x over 1 factorial. The next term we get x squared over 2 factorial, and then x cubed over 3 factorial. If you just write a few terms, that should be enough. You don't have to write all of them. But keep in mind that there are infinitely many terms here because n goes from 0 to infinity. We're going to take series, plug into the limit. So that will be limit x goes to 0 of 1 plus x over 1 factorial, that's just x, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and it continues. So that's e to the x, minus 1 minus x, divided by x squared. The benefit of this Maclaurin series is that we have a positive 1, then we subtract 1. We have positive x, we also subtract x. So those all cancels. So they end up taking the limit of x goes to 0 of 1 over x squared times x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and it continues. And if we keep simplifying by distributing the x 1 over x squared into the parentheses, so we get limit x goes to 0 of x squared over x squared is 1, so we get 1 over 2 factorial, plus x cubed over 3 factorial times 1 over x squared, that's x over 3 factorial, x to the 4th over 4 factorial times 1 over x squared, so that's an x squared over 4 factorial, and it continues. So all the terms that I'm not writing out, they always have an x in the numerator. As x goes to 0, this term, because x is in the numerator, so that x goes to 0. This x squared also goes to 0. All the terms that I didn't write out, they always have an x in the numerator, so they all go to 0. We just end up with 1 over 2 factorial, which is 1/2. That's a limit. If you use L'Hopital's rule, you're going to end up with the same after using the L'Hopital's rule twice. Any questions about this example about finding the limit? Okay, so here's a question: where do we get the -1 minus x at the end? That's in the given question. So the question says evaluate this limit. It has e to the x minus 1 minus x in the numerator. Any other questions? So just keep in mind that when you see questions like finding the limit on the optional homework, you know, if you look at it, it might be difficult to take the limit, but maybe look at some parts of the expression, see if you can rewrite it using Maclaurin series or Taylor series. Usually the Maclaurin series, probably the one that you're going to need to rewrite it, and then some terms will cancel because of subtraction or addition, and then you can take the limit. All right, so some of you are thinking about a question. So here's another question from the homework, more recent, the homework that's due Thursday. The question is, we're going to find Taylor series for f of x equals sine x with a equals pi. So we basically want to find the Taylor series at x equals pi or a equals pi, doesn't really matter. And then we want to find radius of convergence. All right. So I think Chris asked this question. So Chris, I'm going to ask you to tell me in the question, do we represent the answer using sigma notation or just the expanded form, like listing the 4 terms?
Yeah, it's sigma.
Sigma, what is the first value for n? Is the n equals 0?
Yep.
Infinity. Okay. So we want the answer to be in the form of sigma n from 0 to infinity. So that's what we want the answer to be in. So I'm just going to follow what we did before. Just when we find Taylor series or Maclaurin series, we need to know the derivatives evaluated at given a, right? So recall that Taylor series. So recall Taylor series has a form f of the nth derivative with a being the input divided by n factorial x minus a to the n with n from 0 to infinity, right? So we need a lot of derivatives. We don't need a whole lot, I don't know, tons of them, but let's just begin with the first one. So I saw Sam did this, which I think is really good, by making a table. So on the left, you can just keep the f of x, sine x, then you keep the derivative, and then the second derivative, just write those function on the side first. So, and then third derivative, fourth derivative. just list a few until you see a pattern. So f of x equals sine x, the derivative will be cosine x. The derivative of that will be negative sine x. And the derivative of negative sine is negative cosine. And then the next derivative will be positive sine again, right? It's a negative of negative sine. And then those just derivative with x in it. Then you're going to plug in the value a for each for x to find out the f of pi, f of a, in this case, f of pi, which is sine pi, and then f prime of pi, f double prime of pi, f triple prime of pi, and then f to the fourth derivative of pi. It's good to keep it organized this way. I like it. So f of pi sine pi equals 0, cosine pi is -1, and the negative negative sine pi is again 0, negative cosine pi, that's a -1, it's +1, and a 0 again. And if you repeat this pattern, the next term, not that you really need it at this point, kind of helps, right? For the next term, it will be 0, -1, 0, +1, 0, -1. It repeats. Right. So those are the f to the nth derivative of a. Let me just make sure I'm not missing any questions at the same time. Okay, so now let's take those, and so there's a couple of things you could do. For this problem, it's probably easier if you just take them and then put it in the expanded Taylor series form first. So Taylor series with this for sine x. So that will be sine x equals, when we put in 0, we get 0, plus -1 over 1 factorial x minus pi. But the next term has 2 factorial in the denominator, but it's a 0, so plus a 0 over 2 factorial x minus pi squared. That will just become a 0, so eventually we're going to drop it. The next term was +1 over 3 factorial x minus pi cubed. And then the next term is 0 over 4 factorial. I'm going to skip that part. And then the next term will be -1 over 5 factorial x minus pi to the 5th power, and then continues. Right? When we eventually want to write using sigma notation from n equals 0 to pi to 0 to infinity, we don't want all the 0 terms. So all the 0 terms, we can just drop them, just forget about them. So I'm going to write down what I have that's not 0. So I get -1 over 1 factorial x minus pi to the 1st power plus +1 over 3 factorial x minus pi cubed, and then -1. I'm going to keep it as a +(-1) over 5 factorial x minus pi to the 5th, and it continues, right? And then remember, the answer we want to give, the form at the end, should be in the form of n from 0 to infinity, which means the first term here, this term corresponding to n equals 0, the next term corresponding to n equals 1, the following non-zero term corresponding to n equals 2, right? So it's not exactly as the series we had before. We in the expanded series, when I wrote, if we just follow the definition of Taylor series, so this is n equals 0, this is n equals 1, this is n equals 2, n equals 3, n equals 4, right? That's what we have. But we shouldn't keep the 0 terms in the series. So when we write down a final answer, we should drop all the 0 terms and reorganize the terms in terms of n equals 0, n equals 1, n equals 2. But just keep in mind that they're not exactly the same as the general formula for Taylor series here. So how do we figure out the formula for the sigma notation? That usually you kind of have to look at it. So in the one I boxed in blue, so there's a few parts that we have to pay attention to, right? That changes. So we have -1 become +1, become -1 in the numerator. So the -1 alternates, right? And then the next one will be +1, which means when we work on the -1 part, we just write -1 raised to some power n or n-1 or n+1. You have to decide which one it is. In this case, we have n equals 0, give me -1, n equals 1, give me +1 in the numerator, n equals 2, give me a -1, which means if I just put n there, I'm going to have a problem, because if I put 0 in there, I get -1 to 0, it's actually positive, but I want it to be negative. So that should be n-1 or n+1. So note, if we have +1, we have -1, +1, -1 alternating, or -1, +1, -1, +1 alternating, we're going to have -1 raised to either n or -1 to the n+1, which is the equivalent form of -1 to the n-1. So we're going to have to use one of those three in the sigma notation to represent the alternating of signs. You can try one if it, and then plug in n equals 0 or n equals 1 to see if it works. If it doesn't work, try the other one and check. Right, so that's +1 -1. What else? Well, in the denominator, we also have 1 factorial, 3 factorial, 5 factorial. So we got 1 factorial, 3 factorial, 5 factorial. So some number factorial. But how is 1, 3, 5? 1 is related to 0 for n, 3 is related to 1 equals n, 5 is related to 2 equals n. So you have to think about on the side, how is n equals 0 corresponding to 1? How is n equals 1 corresponding to 3? And the n equals 2 corresponding to 5. What's the relationship between the values for n and the values in the factorial? Right. So I think you can all see the pattern, right? Because 0 to 2n plus 1 exactly. So the relationship is that the number in the factorial on the right is always going to be 2 times the number n plus a 1. So 5 is 2 times 2 plus 1, 3 is 2 times 1 plus 1, right? So it's 2n plus a 1 will relates n to the number in factorial. So in the denominator, we write 2n plus 1 parentheses factorial. Again, after you write it down, you can always check, right? If I have n equals 0, do I get 1 factorial? Well, if I put 0 there, I get 2 times 0 plus 1, that's a 1 factorial. Perfect. If I put 1 there, I get 3 factorial. Excellent. Right? And then what else is in the formula? Each of the term also have x minus pi raised to some exponent. And the exponent has a number that matches with the number in the factorial. So if you figure out the number in the factorial, you should be able to figure out the exponent, right? Because 5 corresponding to 5 in the factorial, 3 in the exponent corresponding to 3 in the 3 factorial. Since we already figured out how they are related to n, we can just use that relationship directly. So that will be x minus pi raised to the, what's the relation? 2n plus 1 in exponent. So that will be the formula in the formula in sigma notation for the Taylor series expansion. Does that help? Any questions on this? On sort of like writing the sigma notation representation for the Taylor series. So this is the expanded form. This is the summation notation or sigma notation. Any questions? But I think so one of your classmates, Sam, I saw the work he did was making a list that is very helpful to keep it organized. So you can try to follow that. All right, so here's another question.
How would you find the radius of convergence?
Oh yeah, I forgot about that. To find the radius of convergence, so we're going to use the ratio test. So we're going to set L equals limit n goes to infinity absolute value n plus 1, so that'll be -1 to the n plus 1 plus 1 n plus 2. Divide by 2n plus 1, but n become n plus 1, so 2 times n plus 1 plus a 1 factorial, and the x minus pi to the 2n plus 1 plus a 1. Divide by, so in this case, I'm going to kind of skip that first step. So when we divide by the an, we multiply by the reciprocal, so that will be 2n plus 1 factorial, divide by -1 to the n plus 1, x minus pi to the 2n plus 1. Okay. And then we're going to simplify. After we simplify and take the limit, we just force everything. So we want this expression, we want L to be less than 1 in order for the series to be convergent, right? So that's what we want, keep in mind. So let's see. All right, I'm going to do this way. So that will be limit n goes to infinity. This is -1 to the n plus 2, so that's a -1 to the n times -1 squared. You can just put it all together. I think this might be more straightforward to some of you. So that's a 2n plus 2 plus 1, 2n plus 3 factorial times x minus pi raised to the 2n plus 3. So I'm going to write as x minus pi to the 2n, x minus pi to the third power, multiplied by 2n plus 1 factorial, -1 to the n, -1 to the first power, and then x minus pi to the 2n times x minus pi to the first power. This is just the way I like to write it to make it easier to cancel terms and see what's going on. So if we take the limit, just cancel as much as you can. We have a -1 in the denominator, but we also have a -1 square. So you can either find the square, make it +1, or cancel them with the -1 in the denominator. It doesn't really matter here. It's just -1. So you can just say, okay, this become +1, right? This one just -1 in the denominator. Let's just keep it there. And the x minus pi to the first power in the denominator with x minus pi cubed in the numerator. So that cancels, give me x minus pi squared. And then we also have what? We also have the factorial. To simplify further, I'm going to rewrite this factorial, 2n plus 3 factorial. I'm going to write it as 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n 2n minus 1, as you expand this one, you can notice that this expression from 2n plus 1 to the end, that just basically that is equivalent to 2n plus 1 factorial. So we have limit n goes to infinity. The numerator, what do we have? We have x minus pi squared. I'm going to put it at the end. We have 2n plus 1 factorial times x minus pi squared. Denominator, we have 2n plus 3, 2n plus 2, 2n plus 1 factorial, and then we have a negative 1 remaining. Keep the absolute value. So now we can simplify this term. And then the rest is about taking limits. Limit has n goes to infinity, which only the terms with n will be affected. The term with x and the constants are not affected when we take the limit. So we can separate all the terms that doesn't depend on n, we can put it aside before we evaluate the limit. So now we have limit n goes to infinity, absolute value 1 over 2n plus 3, 2n plus 2, those are the terms has n in them. Multiply with absolute value x minus pi squared divided by negative 1 in the denominator in the absolute value. You can obviously make it a positive 1 by dropping the absolute value, but make sure you actually do the work correctly. The first absolute value, when we take the limit as n goes to infinity, it approaches 0 times x minus pi squared. I'm going to drop the absolute value because the square is positive and the denominator negative 1 in the absolute value, we can make it positive. So that just becomes 0. So L equals 0, right? For any number, for any x value. So we know that 0 is always less than 1. So that means it's going to be less than 1 for all x value. So this is a special case. Whenever we have the x could be any number, then the radius of convergence is going to be infinity. So that's the radius convergence for this problem. If you don't have this, if you end up, let's say you did everything correctly, at the end you have x minus pi squared, absolute value, that's a limit, right? If that's the case, then you're going to, I'm not going to put a square there because that might complicate the problem. Let's just say you have x minus pi at the end as a limit. How do we find the radius of convergence? We just set it less than 1. And this expression is in the form of x minus a absolute value less than r. Right, so it's x minus pi less than 1, which means the 1 there corresponding to the radius of convergence. So that's the radius of convergence if you end up with x minus pi in an absolute value at the end. But the actual problem, we end up with a 0, which is always less than 1 for any x. So that means all x values will make, it doesn't matter what it is, we always make the series convergent. So the radius of convergence is infinite. Questions on this?
Let's say you get less than 1.
All right.
Professor.
Yeah, sorry, I wasn't able to hear you clearly. Go ahead.
If it were to be less than 1 and it's not 0, would it still be infinity?
Yeah, if you, I didn't quite hear everything you said, but I assume that you said if the limit, if at the end the L after we take limit, it's a number less than 1, but not 0. So let's see, L equals 1/2. And yes, that will also be infinity because 1/2 is always going to be less than 1. Right. So assuming that the L is going to be 1/2, doesn't matter what X is. Is that what you're saying?
Yeah.
Yes. So if you end up, let's just say at the end, you do all the work, you end up just with 1/2 after we take the limit. There's no X there, just 1/2. That will always be less than 1. So the radius of convergence is infinity. But if you end up with, let's say you end up with L, after you take the limit, you get L equals 1/2 times absolute value X minus pi. I'm just going to use X minus pi as an example. If you end up with this, right, you have to set this expression less than 1. Because that's when the series will be convergent, right? When L is less than 1. And from here, you have to solve for X minus a less than R form. So you multiply by 2. So absolute value X minus pi, absolute value less than 2. I multiply by 2 on both sides to get rid of the half. So now this is in the form of X minus a, absolute value less than R. So the 2 will be the radius of convergence. I hope it helps. All right, so Daniel has a question about power series. So the question is, find the power series for x squared over x to the 4th plus 16. So this one, we're going to find the power series representation. To do that, I'm going to go back to my notes and write down something that we have done before. So in previous lectures, we had an example that's if we have 1 over 1 minus capital X, that we can write as sigma n from 0 to infinity capital X to the n. Right? And this is convergent if capital X in an absolute value less than 1. So that's a very useful when we try to find power series for a function like this one given, because we can try to manipulate it, make it looks like 1 minus x, capital X. So the x squared in the numerator, let's just put it away. We don't, the numerator, if we sort of put the x squared on the side, we already have 1, right? So we're going to take x squared over x to the 4th plus 16. We're going to manipulate this so that it looks like x squared times 1 over x to the 4th plus 16. And I'm going to rewrite it by flipping the number with x to the 4th. So I'm going to write as 16 plus x to the 4th. The denominator, I just changed the order, the order there. The numerator, I put away the x squared. So that will be x squared times 1 over, I want a 1 there in the denominator. I don't want 16. So I'm going to take out a 16 from the denominator. So that will give me a 1 plus x to the 4th over 16. Right? And the 16 I put out, I'm going to pulling it out and put it next to x squared. I'll put it below x squared. So that will be x squared over 16. I don't need this part for now. I'm going to only focus on 1 over 1 plus x to the 4th over 16. That's the part I'm going to use. So we're going to find the power series for this part first, because that's like a 1 over 1 minus x. Pretty close, right? In that form. So power series for this, and then we're going to multiply with the terms in front of it. So I'm going to continue to rewrite this. So that will be x squared over 16 times 1 over 1 minus, I want it to be 1 minus. So 1 minus what? 1 minus negative, because we have a positive sign, x to the 4th over 16. And then we're going to find the power series for this, because using the formula, because this looks just like 1 over 1 minus capital X, right? So the capital X is equivalent to the parentheses part. So capital X is equivalent to negative x to the 4th over 16. And if we have it, we can just put into the other side to figure out the power series for this, this part I boxed in yellow. So now that will become x squared over 16 times this expression we can write using power series. So that's a n from 0 to infinity, capital X, but capital X is negative x to the 4th over 16 to the power of n. And then we can continue to write this, because keep in mind that whenever you have a sigma notation, it's always good to separate the negative 1 in the exponent on in the numerator or the denominator, separate the negative from the rest. So that's what I'm going to do next. I'm going to keep the x squared over 16. In the sigma notation, I'm going to separate the negative from the rest. So that will be negative 1 to the nth power, x to the 4th power raised to the nth power. The denominator, I have 16, so I'm going to write as 16 to the nth power. So we basically distribute the exponent n to negative 1 to the x to the 4th, also to the 16. So they crowded. So that's what we did. And then we're going to continue with this because now we can actually, since we have the x term separated from the 16 from the negative, we can actually bring the term in front of it inside the sigma notation. So that will be sigma n from 0 to infinity, negative 1 to the n, x to the 4th power times n x to the 4n, divided by 16 to the n. And then when we put it inside, we get x squared over 16. They're all multiplied. Now I just multiply all the terms together. So we end up with sigma n from 0 to infinity, negative 1 to the n, x to the 4n plus 2. When we multiply the two x terms together, 16 divided by 16 to the n times 16 in the denominator, so 16 to the n plus 1. I believe this is a correct answer for the power series. Excuse me. Questions on this problem?
To find the interval of convergence, what would you do again?
To find the interval of convergence, you can try to use a ratio test, you can also try to use the fact that I wrote on the side here in the blue there. So for the function 1 over 1 minus x, right, we write as sigma. That is convergent if absolute value of capital X is less than 1. We can use that fact to find the radius of convergence. So that means when I did this, when I did the substitution there, which is, let me box it in purple. This part, right, I follow the pattern, did the substitution. When I did this, that means this is convergent. This series is convergent if negative x to the fourth power over 16, this is what capital X is equivalent to, if this one is less than 1, right? So that's when the series will be convergent. We're going to use this part to find the radius of convergence. I believe that's correct. So I'm going to put the work on the side. Correct me if I'm wrong here. Could be wrong on this, then I have to double check and get back to you. So absolute value, capital X is negative x to the fourth over 16. We want it to be less than 1 for the series to be convergent. And then we're just going to multiply by 16 on both sides. So we get absolute value of negative x to the fourth less than 16. And drop the negative, become x to the fourth less than 16. Take the fourth root. Because again, we want to be capital X minus a, as in we want capital X, sorry, lowercase x minus a less than r. That's what we want. So take the fourth root. So that will give me capital X, just lowercase x in absolute value less than fourth root of 16. That's a 2. So that's the same thing as x minus 0 less than 2. So the 2 is the radius of convergence. I'm not going to try the other approach, but for some of you, if you want to try it, try with the ratio test. So let me just note to find radius of convergence. Try L equals limit n goes to infinity an plus 1 over an in absolute value. Try that with this an at the end.
So if the radius of convergence is 2, does that mean the interval of convergence is -2 to 2?
In this case, yes. Yeah.
Okay.
But you might want to also test if, so we know for sure that from -2 to 2, any number in there will make it convergent. But you also want to test if 2 itself or -2 is part of the interval of convergence. So you take 2, put it in for x, and see if that's so. So you also want to check at x equals 2 to see if the series is convergent. Just put 2 there to the 4n plus 2 over 16 to the n plus 1. And also at x equals -2, put -2 in there to see if this is convergent. Similar work. Because you could have the interval to be, maybe including +2, but then including -2, or the other way around, or including both, or don't include both. So be careful there.
So sorry, what would we be looking for if they were at 2 and -2 for them to match, or?
You have to, for at 2 and -2, you have to see if the series you get when x equals 2 to see if the series is convergent or divergent.
Okay.
If the series when x equals 2, if it's convergent, that means 2 is part of the interval of convergence. If it's divergent, it's not part of it. Because when we just say -2 to 2, we don't include 2, right? We don't know if the endpoints, the endpoints of x values will also give you convergent series. We don't know, but in the middle it is. All right, so Sam has a similar question on this. Sam, I think I'm not going to do all the work. I think I'll just explain a couple of steps. So it's power series, finding power series for 8/19 plus x, right? So again, the first step, what we're going to try to do is we're going to try to make it looks like 1/1 minus capital X, because we know this will give us capital X to the n. Then we can just substitute in there, right? So if we can make this look like this, we're pretty good. So what we do is we're going to take 8/19 plus x, just like we did before. We're going to manipulate. The first thing we want the numerator to be 1. So you can divide by 8. That's one way. Or you can just put 8 aside. Become 8 times 1/19 plus x. And then the denominator, I want to have 1 minus something. So I want to have a 1 to begin with, but I have 19, so I'm going to factor out a 19. So I have 8 times 1/19 times 1 plus, when we take out a 19 from x, we get x/19. And almost, right? So the 19, we took it out, or we can just put it next to 8. So we get 8/19. It's just a constant. It doesn't really affect anything at the end. That times 1/1 plus x/19. But I want to have a negative instead of plus. So I'm going to write as a minus negative. So the next step is focus on finding the power series for this part using the formula, because it's really just 1/1 minus some big chunk, right? So you can think about this in the parentheses. This part is the same thing as a capital X. Then you can find the power series for this part. I'm going to let you do the work. It should be manageable. And then you still have 8/19. And in the power series, you might have a -1 somewhere. Make sure you separate it like we did before. What I did over here is I separate the negative from the rest. So I write as a -1 to an n power, and then write an x to the 4th to an n power, and then any denominator, I keep it alone with the n power. So you're going to try to do the same thing. And at the end, you're just going to bring this inside, right, as sigma, whatever the constant you have, you multiply with 8, multiply with 19. So the 8 and 19 will be multiplied with terms that's already in there. All right, so Sam, I'm not going to do the work. I hope that's helpful, at least to help you get started. Try that. If you still have problems on this, maybe ask it tomorrow, or just send me an email.
So what would be on the inside, though, of that next part? I'm just trying to figure out what to do next, because I'm still a little bit confused personally.
Yeah.
We don't have to figure out the problem. I'm just trying to figure out what would be next in there.
Oh, the next step from what I...
Yeah, we don't have to do the whole problem.
The next step is you probably end up with...
No. I'm sorry. Not the next step. Like from the 8/19 sigma, and then what's in the circle. I'm trying to figure out what's in the circle. Would it be x over negative or negative x over 15?
Negative x over 19.
Oh no, sorry, not over 15. Yeah, 19.
And raised
don't
to
know.
raised to the nth power.
Oh, okay, that's right.
The above step, what I circle in yellow color, that is equivalent to x, capital X. So in the power series, you should have capital X raised to the nth power.
Gotcha.
That's why I have this to the nth power. All right, so that problem, I'm not going to finish it. I'm going to let you play with it on your own. Now, here's another example. Make sure I didn't forget any other questions. Okay. I have another question that was asked by a student yesterday. I think was also Sam. So it's also in the homework. So the question is find Maclaurin series of f of x equals natural log of which is the number 1 plus 5x. So write the answer in sigma notation. Write answer. Sigma notations will be sigma from 1 to infinity. So it's a little bit different. It's not n from 0, it's n from 1. Right, so we're finding Maclaurin series is basically a Taylor series, but a equals 0. Right, so keep that in mind. So again, I'm going to follow the trick that Sam did by making a table. So f of x equals natural log 1 plus 5x. I'm going to take the derivative. The first derivative, when we take the derivative of natural log with a function inside, we have to use chain rule, right? So that will be 1 over 1 plus 5x. But we have to apply the chain rule here to take the derivative of the inner part, 1 plus 5x. That should give me a 5. So that's the derivative, the first derivative. I'm going to rewrite this to make it easy for the following step. So I'm going to write as 1 plus 5x to the negative first power. That's a fraction, multiplied by 5. The reason I'm putting it this way, because when I find the second derivative, I can just focus on this part because the 5 is a constant. It doesn't get involved, right? So if I focus on this part to take the derivative, I can use chain rule again. So the second derivative will give me, just focus on the part in yellow. So that will be negative 1 times 1 plus 5x to the negative 2. That's to take the derivative of the exponent function. And then times the derivative of the inner function using chain rule, 1 plus 5x. That will give me a 5. So all those, what I wrote just now, that coming from the derivative of this part I boxed in yellow using chain rule. But then outside, I already had a 5. So I'm going to just write down that 5 from the outside. So here we have 2 5s. And I'm going to simplify this. I'm going to write it as negative 1. I'm going to just put it aside. I don't want to touch the negative 1 for now. And then 1 plus 5x to the negative 2. And then the 5 times 5, I'm going to keep it as a 5 squared. Again, put it aside. The next derivative, I'm going to focus on this part with a negative 2 in the exponent, nothing else. The constants in front and after it, I'm going to leave them. So the third derivative, let me just take the derivative of this part first. So that will be -2 times 1 plus 5x to the -3. But then I have to use the chain rule for the function inside. So that's a 5. So this part in the yellow corresponding to the derivative of the one in the box. But before that, I already had -1 from previous step. I already had 5 squared from previous step. So I'm going to keep them. Remember that constant coefficients, they don't get involved in the differentiation or integration process. So that's a third derivative. The fourth, you can write this as, so -1 times -2. So I'm going to write as 2 factorial because it's +1. It's the same thing as 2, which is 2 times 1. Right, so I'm going to write as 2 factorial. The reason I'm doing it because when I take the derivative again, I will have a -3 being multiplied to it. So it looks like the following step, I have a -4 multiplied by it. So I'm going to write as 2 factorial for now. 1 plus 5x to the -3 times 5 cubed. And then the fourth derivative, again, I'm only going to focus on the part in the box here, nothing else. So that will be -3 times 1 plus 5x to the -4 times 5 coming from the chain rule. And then multiply with everything before. So I get 2 factorial in front of it. And then 5 cubed after that. So this I can write as, now be careful here. So you have a 2 factorial is 2 times 1. -3, I can put the negative in front and also the 3. So become -3 factorial. 1 plus 5x to the -4 times 5 to the 4th power. And we can continue this if we want. So that's the derivative using chain rule. And then now we're going to plug in the value a equals 0. So f of 0, it's natural log of 1, which is 0. When we put 0 in the first derivative, we get 1 plus 0 to the -1 is a 1. So we just get 5. You can write as a 1 times 5 if you like. The second derivative, evaluate it at 0. We have -1 in front of it. Then the middle term in the box, that becomes 1. And then we have a 5 squared. The third derivative, when we put 0 in there, again, the part that I boxed will become 1. So I get 2 factorial, it's a positive 2 factorial. Times 5 cubed. And then the next term, I didn't box it, but in this part, that become 1. So I have -3 factorial times 5 to the 4th. And if, I can continue this, I don't even have to take the derivative. If I follow this pattern, the 5th derivative value at 0, so that will be positive 4 factorial, 5 to the 5th power, and so on. So now I'm going to take this, I'm going to put in the expanded form, or you can, so there's a couple of things, couple of directions you could go. You could generalize this formula and write down the nth derivative evaluate at 0. So that will give you a formula which you can use directly in the Maclaurin series formula. Or you can just write down the expanded form and then come up with the new sigma notation, either way. So let me write down the long way, which is the Maclaurin series expanded. So we get natural log 1 plus 5x. So that will become, the first term is 0, plus the first derivative, which is 1 times 5 over 1 factorial times x. The next term is negative 1 times 5 squared divided by 2 factorial times x squared. The next term is positive 2 factorial over 3 factorial. Oh, I forgot 5 cubed over 3 factorial x cubed. The next term is negative 3 factorial over times 5 to the 4th over 4 factorial times x to the 4th power, and it continues. So that's a Maclaurin series expanded. And we want to write as a sigma notation, but drop the 0 term. So we have the first term is 1 times 5 over 1 factorial times x. The next term we get negative 1 times 5 squared over 2 factorial times x squared. The next term we have 2 factorial in the numerator and the 3 factorial in the denominator. Maybe we can simplify them, right? So what is 2 factorial over 3 factorial? So that's 2 times 1 over 3 times 2 times 1. So just give you a 3 in the denominator. The numerator have a 5 cubed. Then we have x cubed. What about the next term? The next term is negative 3 factorial over 4 factorial. We can follow the same way. So that will give me 1/4. 5 to the 4th, x to the 4th. And you probably wonder, what about the first two terms that have a factorial in the denominator? Well, the 1 factorial is just 1. The 2 factorial is 2. So you can just drop the factorial, make it look like a 1, 2, 3, 4 in the denominator. So now we can try to write down the sigma notation. In this example, they want you to write the sigma notation as n from 1 to infinity. So that means the first term corresponding, the first non-zero term in the expanded form corresponding to n from 1. The next term is n equals 2. The next term is n equals 3, n equals 4, and so on. Just like we did with the earlier example, that when we want to write down the formula for sigma notation, we have to sort of look for the different paths in each term there, right? So each term, they have a positive 1, negative 1, positive 1, even though it doesn't see positive 1, but it's positive, and then the negative 1. So positive, negative, positive, negative, it alternates. So that means we're going to have a negative 1 raised to some exponent. Is it n or is it n minus 1 or n plus 1? If we just put n here, when n equals 1, we get negative 1, but we actually want it to be positive. So we just add 1. What else do we have? The denominator is just 1, 2, 3, 4, corresponding to n equals 1, 2, 3, 4. So the denominator is n. How about the 5? Well, we have 5 to the first power, 5 squared, 5 third, 5 fourth. As you can see that in all the terms, the number in the denominator, the one I have expanded, and the exponent of 5 and the exponent of x are all the same, right? So if you figure out one number related to n, the rest will be the same. So we know the denominator is just n, so that means the exponents will be n for 5 and the x. So that will be 5 to the n, x to the n. You can write as a 5 times x together raised to the n. So in a condensed notation, so there'll be n from 1 to infinity, negative 1 to the n plus 1, divided by n, and then 5x together raised to the n. That's one way. But if you remember, it's difficult to remember all those examples, right? But if you remember, that was in the, you can also look it up in the book. In the book, I believe, let me look at my notes, see what it was. In the book, there was a table about Maclaurin series. One of them is natural log 1 plus capital, I use capital X to distinguish, but the book is just 1 plus X lowercase, doesn't matter. So that is equal to sigma n from 1 to infinity, -1 to the n minus 1, capital X to the n over n. So that's what the book says for Maclaurin series of 1 plus capital X. We can just use this formula because what we are interested in is natural log 1 plus 5x. We can just say in the question we are interested, it's 5x, but that's just like capital X in the sort of in the given Maclaurin series formula, right? So that means the only thing going to change is in the power series, the capital X will change it to 5x. So we have n from 1 to infinity, -1 to the n minus 1, 5x to the n divided by n. That's it. If you apply the formula directly, it's, you don't even have to do the expanded form. You probably wonder, well, they look different. It's actually the same because -1 to the n minus 1 and the -1 to the n plus 1, they're equivalent. They just give you the sign, the alternating sign, going from positive, negative, positive, negative. They're the same.
Quick question: why does n equal 1 at the start and not 0? Because we can't use 0.
You can use 0. It just in the, so online on the website it says find the sigma. It says find the Maclaurin series, and then the answer form it give you is like I forget, I think it was f of x equals sigma n from 1 to infinity parentheses. So you have to fill in this part. So you sort of limit that in the question. It tell you have to choose n from 1. But you're absolutely right. We could write it using n equals 0. Actually, I want to show you that. That's a good point. So I'm going to take this. Let's see if I can copy this. So I'm going to copy and paste it here. Okay, so this is the non-zero terms we had, right? We said n equals 0, n equals 2, n equals 3, and so on. But if you want it right as a sigma n from 0 to infinity, you can. So we just say, okay, we don't want them to go from 1, 2, 3, 4. We want them to go from n equals 0 to n equals 1 to n equals 2 to n equals 3. And then the sigma notation will be n from 0 to infinity. And then we just have to figure out the formula for each term like we did before, right? So the plus minus, we know is -1 to some exponent. When n equals 0, we want it to be positive. So probably -1 to the n. That will work, right? Because when n equals 0, we get +1. When n equals 1, we get -1. N equals 2, we get positive. That works. Now, what about the denominator? Denominator, we had a 1 corresponding to 0, 2 corresponding to 1, 3 corresponding to 2, 4 corresponding to 3 for n, right? So it looks like the denominator is always a 1 bigger than the n number, the value for n. So just n plus 1 in the denominator. And then that will give you the exponent as well, right? So that will be 5x raised to the n plus 1. This is perfectly fine.
And then again, to find the radius of convergence, you would just use a ratio test?
I would say probably use a ratio test to be sure.
Is there any other way other than the ratio test Like you're saying, you're making it seem like there's another way.
There's another way, but I'm not confident that it will work all the time.
Okay.
I'm not going to go through that.
Going back to what you wrote down a little bit earlier, the natural log of 1 plus x, what if that was like x to the, like there was an exponent in front, like x to the 4th or x to the 3rd or something like that in front of the natural log? What would you do then? Would you just keep it like out front of the sigma notation?
Yeah, and then you can bring it inside. So is this, let me just write down what you meant. You probably meant that if you have the function, which is x to the 4th power, for example, natural log of 1 plus x to the 5x, is that what you're thinking?
Yeah.
Okay, yes, that's totally fine. So when you try to find the, I guess, Maclaurin series, right? So because the general formula is Maclaurin series. So you're going to find this part, just focus on the x to the 4th, leave it for now. Just focus on natural log, like you said. So that'll be x to the 4th times the Maclaurin series. I'm going to copy it here because we already have it. So that's an n from 1 to infinity, -1, just this part. That's what I'm copying. -1.
That would be for a power series.
Say it again.
That would be for the power series.
This is power series. The answer that you get is so this is a power series, but we just call it Maclaurin series.
Okay.
It's a special type of power series, right? You find the natural log part first, and then after you find that, then you can distribute the x to the 4th, bring it inside the sigma notation. So that will be sigma n from 1 to infinity. The -1 stays. The denominator n stays. The 5x to the n. You have to be careful if you use the way I'm writing, times the x to the 4th. We cannot combine the two x term here because the first x is multiplied by 5 first. So if you want to combine the two x, you have to separate the 5x to the n first. Separate it as separate it as a 5 to the n, x to the n, and then when you multiply with x to the 4th, you can combine the two x parts. It becomes x to the n plus 4, 5 to the n, and then the rest stay the same. All right, Aiden, you said you had a question on a different one. Do you still want to answer your question, or do you think you can figure it out on your own?
I mean, I'd like to try and get it answered by you. I don't know if I'll be able to answer it on my own, but we can start it if possible.
What is the question?
It is, hold up, I'm pulling it up. I think it's similar to the one we did earlier in terms of like sign, but it's f of x equals 4 cosine squared of x and a equals 0.
F of x equals 4 cosine x
Squared of x. It's cosine squared. And then x
cosine square x.
Yeah.
And evaluate at a equals 0, you said.
Yep.
Okay. So this one, I think I'm going to let you try because it's really about taking the derivative and to be careful with the values you get. I'm going to let you try this, and if you have questions, I'm going to answer tomorrow. And be careful when you take the derivative each step. The 4, just leave it. You get 2. Oh, actually, you know what? Let me point out one thing. Doesn't matter. You can figure it out, I think. So 2 cosine x sine x using chain rule there. right? So I would say just keep it as 4 times 2. Don't try to combine it as the 8. Keep it like this. So the next step, when you take the derivative, again, the 4 times 2 stays, you focus on this part. Take the derivative. And this problem, I think that was Sam had I saw his work when he was asking question. Let me take a step back. So here, instead of write it 4 times 2, I think this will save you a lot of trouble if you write it as, so the 2 cosine x sine x, if you write it as sine 2x using the trig identity, that will save you a lot of trouble later. So that would be 4 times sine 2x. And then when you take the derivative, in the next step, you take the derivative of sine 2x by using chain rule. The 4 stays. So you get 4 times the derivative of sine 2x as cosine 2x times the 2. And don't combine the 2 with the 4, keep them separate. And in the following step, take the derivative of cosine 2x. Again, just focus on that part and then leave the 4 and 2 first. So that would be cosine give you negative sine 2x times 2. But before that, you still have a 4 multiplied. So just multiply by negative. And then after that, you still have a 2 from previous step. You can write as a negative 4 sine 2x times 2 squared. So don't combine the 4 with the 2 squared, just keep them separate for all those steps. And then again, the next step, you focus on the sine 2x, take the derivative and keep with the 4 and then the 2 squared. So I'm going to let you finish this problem on your own. If you try to follow this pattern, you can see that basically the terms with the 2 to the power that always increase by 1 each step. The one with a negative 4 in front of it, with a 4, negative 1. I think that just alternating between positive 4 and the negative 4, if I'm correct. So that number doesn't really change too much. All right, any other questions that's urgent? So Aiden, try this on your own. If you have questions, send me an email or ask them tomorrow.
Sweet, thank you, Professor.
It should be similar to the problem that I had earlier with the natural log, I think. Yes, the natural log example that, one part on the left, the other part just alternating, not really alternating, has the exponent that increase by 1 each time. I think it will be similar. All right. We have one more thing that we should talk about. What really big thing? Just one big example. Let's talk about the nth degree polynomial approximation. So is it okay if I start that? Just try to get it out of the way.
I just got a quick question for tomorrow.
Mm-hmm.
Are we going to be learning more information before the quiz, or are we just going to be like jumping into questions and quiz?
If I cannot finish it today, I'm going to try to finish what I planned tomorrow. Shouldn't take too long. And after that, we can just do kind of like final review question and then take the quiz. hopefully we can finish the quiz early tomorrow. All right, so this is 11.11, the last section, just part of it. So let me write down a couple of definitions. The first thing is called the nth-degree polynomial approximation. Of f. It's also called the nth degree Taylor's series expansion is the same. It just nth degree is not going to infinity. So recall that we had Taylor series expansion for f of x is at x equals a is f of x equals sigma n from 0 to infinity f to the nth derivative of a over n factorial x minus a to the n. So that's the Taylor series expansion. It going from n from 0 to infinity. Right. The nth degree polynomial approximation, it's just a partial sum of this infinite series. So define nth degree polynomial approximation of f. We just define it as f of x equals sigma. Sorry, f of x. T sub n of x is equal to sigma. Instead of using n here, we're going to use just I, but sigma I is the same thing as n. Since we already use n here, so we cannot use it in the sigma in the index for sigma. So that'll be I from 0, just like n equals 0 to all the way to n. You know what? I think I'm going to change the notation, that way it might be less confusing, but it's different from the book. So, I change it, keep it. I'm going to stick with the book because I don't want it to be too confusing. So nth degree polynomial t sub n of x is equal to sigma I from 0, just like n from 0 all the way to n, f to the i's derivative of a divided by I factorial x minus a to the i's power. So all the n being replaced with I because they're really the same. And then the difference between this one and the Taylor series is that this one, it stops at a certain number n. You can pick n to be 2, pick n equals 5. You can just pick an n value. It doesn't go to infinity. The Taylor series, it goes to infinity. So that's the only difference between them. For example, if we want to find the t sub 3x of f of x, that will just be the first 4 terms of the Taylor series. So that will be f of a plus f prime of a over 1 factorial x minus a. And we stop at the I equals 3. So that will be f second derivative of a divided by 2 factorial x minus a squared. And then f third derivative of a over 3 factorial x minus a cubed. So that's the third degree polynomial approximation of f of x. And it's a third degree polynomial because if we look at the highest power of x, we get x cubed. right? So it's a third degree polynomial. It has 4 terms because the first term has x to the 0, right? Constant term. So that's the definition of nth degree polynomial. And I'm going to give you another example. So consider f of x equals e to the x. Okay. And then we know the Taylor series expansion at x equals 0. So we know Taylor series expansion at x equals 0, or the Maclaurin series, is e to the x equals sigma n from 0 to infinity x to the n over n factorial. Right, that's what we already seen before. So the question is, what is the second degree polynomial approximation at a equals 0 or x equals 0? Sorry, at a equals 0. So what is the second degree polynomial? That is just going to be t sub 2 of x equals sigma I from 0, instead of n from 0, I from 0 to 2. You can write as n equals 0, but keep it different in notation wise, of x to the I over I factorial. So instead of having infinity in the top of the sigma, we just have a 2 there. Everything is the same form. And if we expand this, we take 0, put in there. So we get x to the 0 divided by 0 factorial, so that's a 1. And then when we put 1 in there, we get x over 1 factorial. When we put 2 in there, we get x squared over 2 factorial. We can't put 3 there because I stops at 2. It doesn't go beyond 2. So that's the expansion. That's the second degree polynomial approximation. And what about the fourth degree? Polynomial approximation. Of e to the x at a equals 0. So it's pretty much the same. So the question is, it's pretty much the same as Taylor series, just a finite number, not infinity. Exactly. So the polynomial approximation with a fixed, a given degree. Yes, it's just a finite series. It just depends on what the degree is, right? That would fix how many terms that you can add in the series. It's just it's a partial sum of a formal way to see it. It's a partial sum of a Taylor series, not the entire sum, not the infinite sum. So the fourth degree polynomial, so that'll be t sub 4 notation. That would be just from sigma I from 0 to 4 xi over I factorial, and if we expand it, would be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed. This is I equals 3 to 3 factorial plus x to the 4 over 4 factorial. So that's the nth degree polynomial approximation. You probably wonder, why do we talk about this, right? We talk about this because the next part is that we want to know So this is just approximation. We want to know how accurate. So how accurate is this approximation for a set of x values? Let's see, for example, we expand it at x equals 0. We want to know how accurate it is for x from -1 to 1. Okay. So let me draw a diagram to show what I meant here. So e to the x, we all know it looks like this. So that's the e to the x. And then if you plot this, let's just, for example, let's take this one. This fourth degree polynomial approximation of e to the x. If you were to take this function and then this function here, if you plot it, it's going to look similar to e to the x, but it's not exactly going to be the same. You might have, let's see, x equals 0, we get 1, just like the e to the x, but you might have a curve that looks like this. Oops, probably doesn't go below. I'm not drawing it accurately. You might have a curve that's red. So this one is the T4, the fourth degree polynomial approximation of e to the x. And to see, this is x equals 1. This is x equals -1. We want to know for this given set of x values, we want to know how close is the red curve to the original function e to the x. We want to know how good is the approximation there. What is the error there? What is the maximum error? So what is maximum error in approximation? In this approximation, the fourth degree polynomial, because it's not going to be exactly the same. So there will be certain error there if we try to use the fourth degree polynomial to approximate e to the x. So the error is somewhere between the sort of like the maximum distance between the curve. We want to know how big is that the gap, the maximum, difference in the height there. So that's why we talk about this. And also this is easier to compute because sometimes you might have a function instead of e to the x, you might have a function that's weird that you cannot find the actual function and then integrate or differentiate directly, or integrate directly to calculate some quantity. But if you can find some sort of polynomial approximation, and then they are much easier to calculate with, because each of the term is just a x to a power. So you can use them to calculate a lot of things, but if you use them, you only get approximation to the actual problem that you try to solve. It's not the exact value, but you just want to know how accurate is that approximation, so you can minimize that. You can know like what's the error at the end after you calculate some quantity. We just use a simple example e to the x here to show you how this thing works. But in real life, it's some function that you might not even be able to come up with the actual function or integrate it. All right, so I'm not going to be able to finish everything, but let me give you a couple other definitions. And tomorrow, the first thing I'm going to do, I'm going to go through this example, talk about how you can figure out how accurate the approximation is. So the next definition, so for a nth degree polynomial approximation, Tnx, we define the remainder as R, we're going to use a notation R sub n of x, and R sub n of x is equal to the function f of x minus the nth degree polynomial. So the actual difference between the function and the approximation is what we call the remainder. And the absolute value of Rn of x will equal to absolute value of f of x minus t sub n of x. And then this absolute value of R sub n of x, or the right hand side, this is what we call the error of approximation. And tomorrow we're going to talk about how do you, using an example to talk about how do you find out what this number is. But before I do that, let me write down one theorem we're going to use. It's called Taylor's inequality. Which says if the f to the n plus 1's derivative of x, absolute value, so that this is the n plus 1's derivative of a function with x in it. If that's less equal to some constant m, then we know that the capital X, this part, really, so that expression, the absolute value of capital R and the remainder in absolute value will always going to be less than or equal to this some constant m. So let me write down this m is some constant. The m divided by n plus 1 factorial times absolute value x minus a to the n plus 1 for some x such that x minus a absolute value is less than d, less than or equal to d. So that's what the inequality, that's what we're going to use. We're not going to go through the process how they end up with, going from here to there. That will be just approved with Taylor's inequality. It's in the book, I think, but I'm not going to go through it. It's not good use of time at this point. And m is some constant. We're going to try to figure out what it is tomorrow with a given example. But again, just like before I wrote, so this part will give us an error of approximation. Will tell us how accurate it is. If that number equals 100, so we know the approximation could be like 100 units from the actual function. That's not a good approximation. So if this Rn of x, let's see, it's a problem about 100, then it's a very, very bad approximation, right? But if the remainder value is so small at the end, after we find it tomorrow with a given example, if that number is 0.00001, that's actually a really good thing, because that means the nth degree polynomial we pick and the actual function, they're so close together. They're basically, kind of like on top of each other, right? So this will be a good approximation. And tomorrow, I'm going to use that example e to the x with a fourth degree polynomial to show you how do we find out this error there for that given approximation. I know that this inequality probably doesn't make any sense to you. Don't worry too much. Hopefully, after we go through the example tomorrow, this will make more sense. All right, I'm going to stop here. I'll see you tomorrow. If you have any questions, feel free to stick around a little bit longer. Take care.
Thank you.
Yep, bye.
Have a great night, Professor.
All right, take care, Aiden. Yeah, try that problem. If you couldn't figure it out, feel free to ask me tomorrow, either office hour or at after we go through what I have to go through. Then then we can go through your exercise problem.
Okay, sounds good. Thank you again.
All right, bye.